It's my great privilege and honor to introduce Brian Hoskins. I should say Sir Brian Hoskins because he was knighted in 2007. I sort of hesitate to do that because, you know, Americans have kind of an antiquated idea of what a knight is, and we sort of half expect you to show up in full chainmail prepared to rescue us from our government, but I gather that's not why you're here. But seriously, it's a huge honor in Great Britain, and it caps a very large series of awards, which I don't have time to tell you about today. But Brian is one of the true giants in the field of dynamical meteorology, and has come up with some really brilliant ideas like semi-geostrophic theory, which I've gotten a great deal of mileage out of. The whole concept of potential vorticity conservation and invertibility, which kind of married the fields of dynamic and synoptic meteorology, propagation of disturbances from the tropics to middle latitudes, and a large range of other things, and was instrumental in starting the Grantham Institute with Imperial College, right? And spent most of his career at the University of Reading. Great pleasure, and he's a very nice guy, in addition to all of that.
Do I use this one? Okay, thanks. Right, thank you very much, Kerry. I've yet to find what this knighthood brings you, actually. It didn't bring any lands or horses or... I'm told if I pay enough, I can get a coat of arms, but that's not very good either. Now, I did think, actually, when I travel the Atlantic, I might get an upgrade, but I'm afraid that doesn't work either. So, anyway, it's been an amazing day and a half, and I think I've been given a lousy slot here, which is 4:40 or 4:50 time here, 9:50 in my time in the evening. And I think it's amazing the audience is as big as it is now. So I've been asked to talk about the legacy of Jule Charney and Ed Lorenz. Well, the last day and a half, we've heard so much from those who knew the two characters well, and the legacy then extends to the wider field we've heard about this afternoon. And I find that anything I say is just going to be picking up on things you've heard and repetition. Now, I'm reassured somewhat because I did create the slides before I came, so it does suggest I did the right sort of thing. But I should say, unlike many of the speakers, I didn't know the gentlemen Jule Charney and Ed Lorenz very well. I first came across Ed Lorenz when, in 1969, I was doing the last year of my PhD in Johns Hopkins when Francis Bretherton came over, and I went to a meeting in Washington, and there was a certain gentleman from the UK who harangued the audience, and then after that came in this gentle character who strode onto the stage, making no ripples whatsoever, and fixed you with his blue eyes. It was like the Madonna. Wherever you were sitting, those blue eyes fixed you. And he gave the most eloquent, coherent talk, and that was my introduction to Ed Lorenz. And my wife and I and my family did come across him afterwards in summers in Encar, and one of those hiking stories, yes, with my young family. I think there were probably about 4 and 6, my daughters. This was the late 70s. And we were invited to go on a hike with Jane and Ed, and the Boulder winds started. And they were going stronger and stronger, and we reached this wooden bridge that was swaying in the breeze, and some of the slats were missing. And Ed clearly thought this was a very suitable way to bring up children. And we had to crawl over this bridge. But I think Jane took pity on us and said, I think we really should turn back. And for Ed, that wasn't the easiest of concepts. But anyway, we did turn back, and we survived. Now, Jule Charney, I didn't know he was in the audience when I gave the talk at the end of my year in 1970-71 at Encar, the Advanced Study Program, and I gave a talk on frontogenesis. And I'm glad I didn't know he was there, because I would have been far too nervous if I had known he was there. But at the end of it, he took me to the library and showed what I had been calling Ertl potential vorticity should be called Rossby potential vorticity. And so forevermore, it's at least Ertl-Rossby potential vorticity. And he was interested in what I'd been talking about, and that was just amazing to me. And so those were my meetings, but I had a few meetings with both of them, but it really is at a distance, most of my understanding of what they did. Now, the title I've been given is The Legacy. So it's not the legacies, it's the legacy. So that means I should try and draw them together somewhat, and that's what I'll try and do. And so I'll deal with them side by side, but sometimes, particularly if time passes on, then I'll actually deal with them together. And what did Charney bring in terms of the theoretical foundations? Well, I think for me, it is this rigorous approach that made dynamical meteorology very much a respectable part of fluid dynamics. And so the ideas of scale analysis and approximating the equations, and in particular the quasi-dystrophic equations, and then using simple models based on them. So this great rigor brought to the equations and putting it into the tradition of fluid dynamics. And he also was very much in terms of the hierarchy of models that probably I didn't give him enough credit later on when I gave a talk about that and wrote something about that, because he used the whole range of models available to him. He started off with a simple barotropic vorticity equation, quasi-geostrophic, and then up to the most complicated models that were available to him, but he used the whole range. Now, Lorenz, the approach to the models was different. These were more representational models, that often low-order models. And so these models were simple, but not derived from a sort of scale analysis of the equations, but from some inspired way of getting a representation of what went on. And the rigor then really came in at the exploration of those equations. So the rigor really came in at that stage and looked at the dynamical system behavior and really gave the whole framework in which we consider predictability in our subject. Now, if we move on to numerical weather prediction, clearly Charney was the crucial figure at the beginning of that. And on the background had been Richardson's attempt to do this, which was a glorious failure in the best British traditions. So that could inspire, or it could tell you to stay away from it. And when Charney was called on by von Neumann to actually take part in this first numerical weather prediction effort, then the rapid progress there was very much due to Charney realizing that rather than the Richardson approach, he should actually take the simplest model, very much borrowing from Rossby, and make progress on that. And the success there really left its legacy that numerical weather prediction was on the go from the beginning of the computers. And the computer producers designed their computers very much and wanting their first usage to be in numerical weather prediction. So numerical weather prediction was in right at the beginning of computing. And without Charney, I'm not sure that would have been the case. And the rapid expansion of this in the 50s and 60s was really just an amazing follow-on from this early success of Charney, showing it was possible. And this became possible to go beyond the barotropic vorticity equation because of Charney's work in looking at balanced models in general, whether they could be quasi-geostrophic or before that, and filtering out the modes that were not required, the gravity modes, the fast modes. So models that concentrated on the evolution of the slower Rossby-type modes. So he created the models that were used for these numerical weather prediction, and the ideas there were used in the initial conditions as well. And we heard about data assimilation, that actually very much the ideas of data assimilation. He really pushed then also the use of the primitive equations. Now, I've often thought that maybe it's a bit sad the primitive equations were used so early in our subject, because we might have been forced to think about the physical processes and parameterizations in a more balanced way if we'd kept to the balanced models. But as it was from the move to primitive equations, then you could throw almost anything at the model and it would take it. It wouldn't necessarily do the right thing with it, but it would accept it and move on. So if we'd actually thought about the physics in a balanced way, even though the model was a primitive equation, the model helped, but Charney saw the way through to using the primitive equations, and that very much led the way to Joe Smagorinsky and others using them. The choice of an area for a model, then very much guided by the ideas of group velocity. I think Charney had an idea of what sort of domain one should use for this. I think I've heard it just said in Europe, in the UK, that we put our western boundary too close, thinking only of the effective speed rather than the actual speed of which information might move. So ideas of group velocity coming into choosing what domain one should use. And having got all the equations for middle latitudes, he certainly thought about the tropics as well, and the balance in the tropics and the first ideas there, and saw the crucial role for convection and interest in the organization and the role and representation of that convection. But then beyond that, he was also with Shukla very much thinking of the predictability from in the tropics that might be greater because of the dependence on external conditions, whether that be to do with the land surface or the ocean. And this examination of desertification that we've heard about and the positive feedback there, the first use really of examining an Earth system model and looking at the interactions of the components and trying to understand those interactions and how they might give a behavior that's really very different from the sort of weather forecast model itself, this positive feedback. And he didn't mind getting his hands dirty in terms of the discretization of the equations as well. And there was the Charney-Phillips vertical scheme, for instance, and of course the horizontal schemes he'd used before. Now, if I go to Ed Lorenz, then, as we've seen, the background of Ed's work leading to thinking about what is predictable. And the whole approach to medium-range weather forecasting really followed on from the ideas of Lorenz, going on from the initial 1-2 days of the synoptic system to what might be possible for the long waves, not predictable forever, but what is that range of predictability, which Lorenz had talked about. And he'd very much thought about the sensitivity to initial conditions, as we know, and brought in the idea of singular vectors that, again, were brought to the fore later on. The initial error that could cause you the biggest problem later on, and amazing growth rates that can come out of that. And ideas of the stable manifold, and linking across to the Charney things of thinking of initial conditions, etc. And the limits to predictability very much in the earlier range as well. The ideas of attractor and transitive, intransitive behavior, which lie behind a lot of our thinking of the regimes of flow and how one might maintain those regimes or move from them. And ensemble forecasting then, clearly, as Tim has mentioned already, followed Lorenz, talked about it early on, and again, when we became mature enough to understand what Lorenz was talking about, then that's what was put into play. And finally, again, I put the discretization of the equations, because I just saw a paper in the QJ the other day, which was talking about, is the Charney-Phillips grid better or is the Lorenz grid better? We're still discussing the grids that they introduced. And I think it's the approach of these people that they were inspired by the observations and by the need to predict and the need for society for those predictions. And they were going to do the theory. They weren't afraid to get their hands dirty with either how to put those equations into a computer or running the computer. So we got the whole gamut from them. Now, in terms of legacy in our subject, I put this as some other examples, but Charney baroclinic instability. I mean, it's hardly another example. It is a major example. Eric Eadie was doing similar things in Britain, a very different sort of character. I'm not sure that his calculations would ever have come to light unless Charney had been around and in the visits to Norway with Aunt Elias, etc. Whether Eric Eadie would actually have published what he'd done, I'm not sure. But certainly the ideas were there, and Charney's work there is crucial. And then the Charney-Stern stability criterions. It was different models gave different ideas of what were the stability criterion, but then it was all unified in the Charney-Stern stability criterion. Stationary waves, Charney and Listen made amazingly realistic view of what the mountains might force in using a barotropic model. And as has been said before, many of us have been chasing over the years the stationary waves, trying to do better than the Charney-Elias model, which was just barotropic, and looking at the forcing by the thermal forcing as well. And the ideas of multiple equilibria came in there, again, perhaps rather easier in a channel than it would be on a spherical domain, but very interesting ideas as well. And the vertical propagation of planetary waves we've heard about, interesting in terms of the domain one uses for any sort of numerical weather prediction, but then crucial, obviously, for the stratosphere. And geostrophic turbulence came in there. So perhaps I'll talk about that when I get Lorenz up a moment. And we've heard oceanography as well, some major contributions there. Lorenz came up with this available potential energy, seemingly to the rest of the world from nowhere. This beautiful paper came out on available potential energy, and people have been following those ideas for many years since. Like Kevin Trenberth, starting my PhD in 1967, the general circulation monograph of Lorenz was crucial to me to actually read this coherent, beautiful account of the state of knowledge of the general circulation at that time, and also work on the stability of barotropic planetary waves I've put in there. Following from those, actually, you can look on the GFDL formation very much as being stimulated by the work of Charney and his linking with Smagorinsky and the formation of the Institute. And even in NCAR, he certainly played a significant role. And I think Lorenz's ideas very much led to were input to the whole idea of the ECMWF, what was possible in the medium range and how that could be taken forward. And Lorenz actually linked with them quite a lot in terms afterwards of how those ideas were developing of what might be predictable. In a wider world, I think we must recognize Charney. Charney saw the birth of the computers and then the birth of the satellites that were able to observe the world. And he put this together very much more than anyone else, I think, that this provided a new opportunity. But it only provided an opportunity provided the world actually worked together and collaborated together to understand more the things we didn't understand and to work together to drive this forward. So we've heard about GARP, the Global Atmospheric Research Program, and its first weather experiment, and FIGI. And really, the World Climate Research Program then derives from that. And then, so that's part of Charney's legacy. But it actually comes also this report on carbon dioxide and climate, because there we saw the germ from which we got the UNFCCC, the IPCC, and the Paris Agreement, all following on. So major contributions on the international scene there. Lorenz, we've heard many of the ideas this afternoon. What a major contribution, the forced dissipative chaos, a fundamental concept in science. My daughter the other day, she's now 44, I think, and sort of fairly high up in the company, she went to something in Singapore, and someone was talking about encryption. And she said to him afterwards, well, I actually have met Lorenz. She didn't say on a rickety bridge in a walk at Chautauqua. And he was absolutely amazed, and he brought his friend over to meet this person who'd met Lorenz. An amazing impact on the world. and this idea of simple system equations and complex behavior. So we have then these two very different characters. We've heard about this. One, extrovert, exuding confidence, charismatic, and the other, quiet, self-effacing, but by no means, when you saw those blue eyes, you certainly knew there was something there. And one I've characterized as enjoying dancing and tennis, maybe that's a slight, and the other hiking and skiing. So there's two very different people there. I think we've heard already that they were combined in their greatness in terms of their integrity, their scientific greatness, and their humanity. So they had a lot there, but I think it really is a help to the inclusiveness of our subject that we have two great people who are able to lead, and they are so different characters. There's room for everyone in our subject, and it is an amazing subject for the friendliness of inviting contributions from such a wide spectrum. And finally, I wanted to actually say, well, clearly is an inspiration. Both these people were an inspiration to those who followed them at the time, but they were an inspiration to many of us who followed on. And I'm showing one picture that I dared not show to anyone from MIT before, but this is actually from the 26th of October, 1969, when I was in Baltimore. My wife and I were in Baltimore, and we went to visit friends in Boston. And that, you may not recognize, that's me in the right-hand corner there. And I didn't know where the department was, but my wife and I insisted I had to come and see MIT, the home of the gods. And this is me kneeling down before. I didn't actually visit the department until many years later, and I hadn't met the people at all. But that's what it meant for me. This was the home of the gods, and that's the legacy of these two great characters. I think I'll get rid of this picture, actually.
Do we have any questions for or remarks for wonderful presentation?
Thank you.
I mean, you have very clearly explained the legacy of Ed Lorenz, especially to our field. From 1985 up until his death in 2008, Lorenz kept working, even after his retirement. Most of the time, he devoted his research to nonlinear dynamical systems. In our field, we may not know many of those papers, actually, but they're all wonderful piece of work. He published many papers, but he concentrated on nonlinear dynamical system, especially on describing structure of the chaotic attractors, quantification of the predictability and things like that. I don't know what legacy that would leave, but many of them are very fascinating papers describing in detail the bifurcation sequences and the structure of attractors.
Thank you.